evening, everyone. I, Dhruvi Singh, Secretary IEEE, warmly welcome you all to the fifth day of the development program on electric vehicle powertrain simulation using MATLAB and real-time simulator. I would like to extend a heartfelt welcome to Professor Sanjeev Kumar Sir, Coordinator HRT Cell, Convener FDP, and also our expert speaker for today's session, along with all the distinguished faculty members present here. We shall now proceed to today's highly significant session on MATLAB simulation of reduced device count MLIs for electric vehicle. Participants will gain practical insight into designing and simulating a reduced device count multi-level inverter in MATLAB for efficient and high-performance electric vehicle applications. Our expert speaker for this session, Dr. Sanjeev Kumar Sir, is a professor in the Department of Electrical Engineering at HBTU Kanpur, currently serving as Dean of International Student Affairs and coordinator of the HRD cell. Over 23 years of academic and industrial experience, he has made significant contributions to the field of power electronics and electric drives, particularly in multi-level inverters, high power converters, and electric applications. He obtained his PhD from IIT Roorkee in 2016, focusing on performance enhancement of multi-level inverters for induction motor drivers. He also completed his MTech from IIT Roorkee with a specialization in power apparatus and electric drives, and his BE in electrical and electronics engineering with first division from NJP Rohilkhand University. He has begun his career in industry working with the Indo-Canadian Consultancy Services, EMA India Limited, and Global Electech Limited, gaining hands-on experience in automation systems, PLCs, SCADA, CNC systems, and industrial drives. Since joining HBTU in 2007, he has progressed from assistant professor to professor, actively engaging in teaching, research, and academic leadership. His teaching spans from undergraduate and postgraduate courses, including power electronics, electric drives, and advanced power converters. Dr. Sanjeev Kumar Sir has an impressive research profile with multiple publications in reputed SCIE and Scopus Index journals, including IEEE transactions. His work focuses on advanced inverter topologies, electric drive systems, and their industrial applications, particularly in sectors like sugar industries and electric mobility. He has also authored books and contributed to numerous international conferences. He has received several recognitions, including the IEEE Outstanding Branch Counselor Award and securing an All India rank of 162 in GATE 2003. A senior member of IEEE and fellow of IETE, he actively contributes to professional communities and serves as faculty advisor to Electronic Society's Student Branch chapter at IETU. Dr. Sanjeev Kumar Sir has supervised several PhD, MTech, and BTech students guiding research in emerging areas of power electronics and renewable energy systems. He is also actively involved in organizing faculty development programs, workshops, and technical events and has delivered expert lectures at premier institutions. His technical expertise includes MATLAB, ETAP, and industrial control systems. He is committed to promoting practical learning, innovation, and industry oriented education among the engineering students. With this, I would like to request Dr. Sanjeev Kumar Sir to kindly take over the session.
Thank you, Dhruvi, for such a wonderful introduction. Before starting, I am thankful to all the participants who have voted yesterday, as I have put it one poll that whether they want a lecture on MATLAB or on the presentation base or both. So most of the participants said that lecture must be based on PPT as well as MATLAB. So I have considered the same as you poll. Let me share the screen. Just give me a second. I hope my screen is visible to all of you. Hmm. My screen is visible. Can anyone confirm?
No, sir.
It is not visible.
Yes, sir.
Okay, thank you so much. Okay, the topic of my talk is this MATLAB simulation of reduced device count multi-level inverters for electric vehicle in 1 week FDP on electric vehicle powertrain simulation using MATLAB and real-time simulation. As this is the fifth day and we have talked a lot about the charging infrastructure, various type of charger for battery, but ultimately we have to run the an electrical motor, right? So to run that motor, we required, if it is an induction motor, we required inverter, right? The basic configuration is like this, that one uncontrolled bridge rectifier, we generate the DC link and that DC link is fed to the inverter, and after doing proper filtration we just run our three-phase induction motor. If we use two-level inverter, then problem of high dV by dt and harmonics, all those problems occur. Not only that, that common mode voltage is another challenge for the researcher. So to do this, we go for open and winding based induction motor. This open and winding based induction motor is nothing, but what we did, we simply uh, open the neutral. We simply open the neutral. My PPT is visible. My PPT is visible or not?
No, sir.
No,
It is
sir.
not visible. Arey, just a second. I don't know why it is not visible. Now just check. Is
Yes,
it
it is
visible?
visible. Yes, sir.
Fine. So, so slides are changing.
Yes.
Okay.
Yes.
As I said, the topic is MATLAB simulation of reduced device count multi-level inverters for EV, and the configuration is like this. We have uncontrolled rectifier, then DC link, after that inverter, and it is feeding to the induction motor. As two-level inverter suffers from various problems like high dV by dt, switching losses, and common mode voltage. So to overcome this, we use one is this open and winding induction motor. In this, what we do, we simply open the neutral and fed the motor from both sides. You might remember the topology which Dr. Behra discussed, right? So in that way, it is going on. This open and winding induction motor, it requires two inverter because we are feeding both sides, right? Stator is open and now it is having six terminal and three terminal is fed from one side from one inverter and other one is fed from another inverter, right? The benefit of this open and winding based induction motor, right, particularly in EVs, and the first and most important thing is that battery size is reduced. You can use the two small battery rather than having the big battery. That is the one advantage of this, right? So the utilization of DC bus voltage is quite high. As if you compare the fault tolerance parameter, see, there are two inverters. So in case if one inverter is get fail, then you can use the second inverter, right? If we talk about the performance, a wide range of speed you can achieve with this. At the same time, the harmonic content of the output voltage of the inverter is quite low, and reduced DC-link voltage requirements are the few advantage of open and winding induction motor over the normal induction motor. And I request to all participants, the moment my either my voice or my PPT is disappear, please let me know. It should not be like monologue. I keep on talking, and after 30 minutes you said, sir, your PPT is not visible, right? So that type of thing should not be happen. Now, if we talk about the control strategy of open and winding induction motor drive, we use the space vector pulse width modulation here, or we can use the field oriented control, or we use DTC, which is direct torque control, or we could use any fault tolerant control algorithm, right? The challenges and which are to be considered, that it requires precise synchronization of both inverter. That is the first challenge which you should consider. Then the control complexity is there as compared to single inverter system, but at the same time that is not a big issue. Reason is, once you program the things, it is automated run, right? And you should that the cost and weight consideration is also another thing. Now come to the fundamental, and see, I will try to finish my PPT very soon, let us say 30 to 40 minutes. Then after that, we will go for this MATLAB simulation. Clear? Now, if we see the configuration is like this. You can see at left hand side that there is one two level inverter having the battery voltage VDC by 2, and the another side of the stator winding is fed by another inverter which is also having the voltage of VDC by 2. So total VDC is the requirement, means DC link voltage is still remains same, which is required in the normal induction motor, right? You are simply feeding from two inverters, so battery voltage is half of the full. Now, if we see this configuration where we use two level inverter, it will give you the voltage performance equivalent to 3-level inverter. Voltage performance equivalent to 3-level inverter. The level 1 is minus VDC by 2, level 2 is 0, and level 3 is VDC by 2, right? So how we achieve this? We achieve this using the switching pattern of the inverter. For example, whenever this one switch is on, the pole voltage VA10 would be VDC by 2. And whenever S14 is on, lower switch is on, the pole voltage would be 0. The same thing is also happening with the right side converter, right side inverter. So the two pole voltage which you can have is 0 and VDC by 2. When you find the phase voltage, which is VA10 pole voltage of first inverter minus pole voltage of second inverter, you will find the level come out to be minus VDC by 2, 0 and VDC by 2. This is the switching table given, right? Now, if we talk about the mathematical modeling of the dual two-level inverter, this is called dual two-level. The name is given because we are using that two inverter. That is why the name is given. So simple, by applying the KVL, you can calculate the voltage of VA1A2, which is the phase voltage. Now, if you see, the common mode voltage is VOO dash. Common mode voltage means the voltage which is occur between these two neutral. See how much the value of this? It is simply 0 because all the time V2AO dash plus VB2O dash plus VCO dash, the net voltage is 0. So common mode voltage If you add all these two, the net voltage would come out to be common mode voltage is come out to be this, right? After putting this value, we will get the phase voltage and everything. And if we talk about the modulation scheme, this here we have used the sinusoidal sine based space vector modulation. See what we try to do, we get the space vector performance. Why we are interested to have this space vector modulation? Because the voltage profile get improved, means you can use the higher means maximum DC link voltage, right? It's 0.866 of VDC, but as the number of level increases, it is very difficult to identify the sector and triangle number and all those things. Those who are working in the field of power electronics, they know what I mean to say. So here we have used a simple sinusoidal based space vector modulation. How we will generate this equivalent performance? This I have taken from the K. Gopakumar sir paper. He was professor. I mean, now he is retired. He was professor at ISC Bangalore. So from there, I have taken this simple. This is the mathematical modeling of this motor and inverter and all those things. How we generate this reference signal? That reference signal is generated by adding an offset. And what is the offset value? The offset value is minus of maximum of VA, VB, VC star plus minimum of VA, VB, VC star. These VA star, VB star, VC star are the three sinusoidal waveform which are 120 degree apart. Normal sinusoidal PWM things are applied. The only difference is we have add this offset. We have add this offset, which is maximum of VA, VB, VC star plus minimum of VA, VB, VC star. That offset is to be added. And this is the simulated model of this. We have also tested on the real-time simulation Opel RT. I'll demonstrate if time permits. So here you can see there is one inverter underscore 1, another inverter is inverter underscore 2, and this open and winding state open and stator winding induction motor. So 6 terminals are fed by these two inverters, and to control this inverter, a modulation index is provided which generates the voltage and frequency. And here we have maintained the constant V by F ratio just to utilize the motor flux fully, right? So these pulses are generated. We will also see the MATLAB model of this. And this inverter is operated at switching frequency of 1 kilohertz for the modulation index 0.2, 0.8 and 1, right? And the corresponding frequencies are 10, 40 and 50. In case if you have any doubt, please ask. That would be great, right? And I advise to co-coordinator Astos and all, please keep on monitoring whether our participant has appeared or not, because today it is not possible for me to check it, right? And feedback form is also to be float in between as per rule, right? Now when this inverter is operated at 10 hertz, this is the phase voltage, phase current and pole voltage, pole current is there. Now if we see the TSD is somewhere around 132.53. It is operated as 2-level mode. Now as you increase, you can see the waveform is improved, and now it is operated at 3-level inverter at 40 hertz, and the TSD is drastically reduced to 32.18. And if we talk about the this current TSD, it is only 10.58%, but still it is quite high as given in the IEEE 519 standard. And once you make the modulation index 1, your multi-level inverter is now operated in the normal 2-level. You can see It is the over modulation range. It is the over modulation range, and inverter is converted. Inverter is now operated simply two level inverter mode, and the TSD and everything is get increased, right? The inverter is also tested for transient state, means when the modulation index is all of a sudden increased from zero point 0.2 to zero point 0.8, you can see the output voltage immediately get changed, whereas the current take few cycle to get settled. Likewise, in the reverse, means when the modulation index is changed from zero point 0.8 to 2, right? There is some typo error. This is changing from zero point 0.8 to zero point 0.2, right? So this is the summary of this type of topology, that the number of level obtained in the dual two level inverter is same as the single three level inverters. And what we are using, we are simply using the two level inverter and getting the performance equivalent to three level, right? And if we talk about the supply, so in case of three level that required three isolated supply, it requires only two isolated supply. If we talk about the diode clamp inverter, it doesn't require any clamping diode. If you talk about the flying capacitors, it doesn't require any flying capacitor as it is required in the flying capacitor topology. See, there are three fundamental and well established topology, that these are neutral point clamp, flying capacitor, and cascade edge bridge. Alright. So all these advantage in the open and winding induction motor. Now, as we have seen that the TSD level was low, so what we did, we further extend one two level inverter. Now, left hand side inverter can have three level operation, like it could have zero voltage, it could have 2 VDC by 4, or it could have 3 VDC by 4. Why I am saying 2 VDC by 4? This is VDC by 2. So it is equivalent to 2 VDC by 4. So the pole voltage of left hand side inverter could be 0, 2 VDC by 4, or 3 VDC by 4. Whenever these two switches are on, that means S21 and S11 would be on, the voltage level would be 3 VDC by 4. Likewise, right hand side voltage could be 0 or VDC by 4. This is the switching table which I have already explained in my previous slide. So the level which we can have are minus VDC by 4, 0, plus VDC by 4, and plus VDC by 2, which is 2 VDC by 4 and 3 VDC by 4. So there is a step of VDC by 4 in every level, right? And this is the space vector diagram of various switching state, right? I'm not going to discuss all this in detail because this is separate field, and if I started talk about this, the entire lecture will be spent in this. So I'm not going in the detail. Similarly, we can properly select this DC link voltage. We can properly select this DC link voltage and can have the same circuit can generate 6 level operation. The same circuit can generate 6 level operation. How? Just see. The left hand side voltage levels are 0, 2 VDC by 5 and 4 VDC by 5. Whereas right hand side could generate 0 and VDC by 5. So the motor phase voltage could be minus VDC by 5, 0, plus VDC by 5, plus 2 VDC by 5, plus 3 VDC by 5, or plus 4 VDC by 5, right? Depending upon the switching which is on. And this is the hardware setup. See, I will try to cover as much as I can. The reason is we all are faculty. We have several research scholars. I just throw some ideas. So if you are interested to do something in this, we can collaborate and do something, right? This is the hardware setup. What we did, this is open and winding induction motor, which is fed by the inverter, two inverters, right? And these inverters are having switches, power electronic switches, IGBTs are used, and IGBT or MOSFET depending upon the rating for which you are going to develop. At present, I have used the IGBT, right? And these IGBTs are triggered or fired, or the pulse is given through the Opel RT system in real time mode. What we did, we generate the program for this Spartan board using the our host PC on MATLAB, and run in this real time simulator. And after measuring the voltage and current and properly design control logic, we generate the pulses which are passes through the isolation circuit. Then after that, deadband circuit, and then go to the IGBT driver and fed to the inverter. Deadband circuit is required because there may be the chances of that short circuit in the same leg. So for that we have provided 4 microsecond delay, and that delay circuit is very deadband circuit is very simple. Using 7404 you can have this circuit, right? So this is the setup. You can see here voltage and current sensing circuit. I'll show the real uh, things. I hope it is visible. These are the current sensor. These are the Hall effect current sensor which are used in this. Here you can see. Here you can see. Right? Now, these are the voltage sensor. These are the voltage sensor which are being used. AD202 base. All the circuit, everything we can share. No problem. It's all for the knowledge sharing. Right? So in case if you require, we will provide everything. These are the voltage sensing circuit. Clear? And if we talk about the IGBT module along with the driver circuit, here you can see this is the IGBT which is having where snooper circuit along with the varistor. Then the driver circuit is mounted on the heatsink. Then driver circuit is mounted on the heatsink like this. The pulses which are generated through the this all these hardwares are visible to you, because I am not able to check whether these are visible or not. Can anyone confirm?
Yes, sir, it is visible.
Visible,
Okay,
clearly
okay,
visible.
fine. So here we have used one boost regulator. Reason is the Opel RT pulse which are generated from the Opel RT is 5 volt, and IGBT required 14 to 16 volts. So the boost converter is used, which generates from 5 volt to 16 volt, and that is fed to the IGBT which is here. Yes. Okay. In case if you have any doubt, you can ask. And this is the simple 5 volt supplies. All these things are generated in the lab. See, I'll also show you the compact circuit of all this, which is readily available in the market. But since we are the teacher and we teach UG student, PG student, and research scholar, at least one time they should make themselves, rather than simple purchasing, doing order on Amazon or some other sites, getting these component ready-madely properly. That will not help for learning. Right? To learn, you should at least design the circuit, then test in or the PSpice or ORCID, generate the PCB layout. Everything they have to make themselves. Then they have full control on the hardware. See, this is the complete hardware setup which is used to experimentally validate the topology. These are the IGBT module which are being used along with the control circuit and the Opel RT system and this open and winding induction motor. Right? All these things are developed in the lab. Now I'll show you one small photograph which is of PhD work of my student. And here you can see the size of two level inverters. The size of two level inverter. We have used 4 2-level inverter for this purpose. That actually we did work on 24. This was the complete drive, right? So and we are successfully published 2 transaction on this topology. Very good publication we get using all these things, and you can see the size of a rectifier and these inverter. These are designed and just giving the order to supplier, and they have manufactured for us. But we have designed the entire inverter circuit and everything, and on chip they have developed. Right? Then this is the especially winded motor which we have developed for this. Here two open and winding based induction motors are used, right? Because this project research work was related to industry, sugar industry. There they use 2 induction motor. So rather than using the simple induction motor, we use the 2 induction motor, and that to the open and winding induction motor, and these are fed by all 4 inverter, and the TLD and everything that improves so wonderfully. So here you can see these are the hardware result which we have to operate our inverter at modulation index of 0.2, and these are the TLD. It looks like that these are the simulated one. No, these are not the simulated one. These are the actual hardware. These are the actual hardware results. How we get this? We have taken from AD202 to the its analog input of the Opel RT, and there after getting these data in real time from the hardware, we made these graphs using MATLAB, right? So these are the real parameter or the real things which we actually practically we receive in the setup. And here the inverter is operated at 0.4 modulation index, and see the TLD is 31%, and still the TLD is not the up to mark, not up to the mark. I'll show you the value of TLD at modulation index 0.8 and frequency is at 40 hertz. What we get, we get TLD of 7.11%. Still, it is not less than 5%. So we go for, and this see the beauty of this Opel RT and all. We get 1-to-1 correspondent between the simulated result and the hardware result. Control pulses are generated on the same logic for which we have simulated, and these control pulses are operated the actual hardware, and we are getting the exactly the same result, almost same result what we are getting in the simulation one, right? Modulation index here is increased from 0.2 to 0.8, and here it is decreased from 0.8 to 0.2. Immediately this voltage level gets settled, but current takes some few cycles to get it settled, right? Now this is the summary of 5-level inverter scheme, that voltage and current harmonic spectrums are improved as compared to D2L, and it is quite obvious as the number of level increase, so the harmonic content decrease, and the performance is of course improved. And again, no clamping diodes are required. All in terms of component, all the advantage which are in the 2-level inverters, this D2L inverter, the same type of advantage are in the 511. It uses no clamping diode, no flying capacitor, less number of DC link, isolated DC link as compared to CHV. All those advantages over the conventionals are there. Now after that we developed the 911 inverter, and there are so many things. Now I really wish to know from the audience whether you want for MATLAB simulation now, or I should continue in the PPT mode, because in yesterday I have asked the first option was MATLAB simulation, the second option was PPT base, and the third option was that demonstration of MATLAB along with some PPT. So I was expected that most of the audience will choose hybrid mode, because the first and second is already included in the third one. But anyhow, I have noticed 4 participants have selected PPT based presentation, 16 said that the live demonstration, and 45 said the hybrid mode, which is brief fundamental PPT plus MATLAB demonstration. But I am not able to understand whether the brief is over or not. So I am asking to you, I should go for MATLAB or I should carry on in this, because so many slides are there. If I complete all those slides, the entire 1.5 hour is I spend in this. In fact, more time is required. So if any participant can tell me that I should go for
Sir,
MATLAB, that would be
sir,
great.
majority of
Yes.
us have selected already for hybrid mode. So we are interested
So
for hybrid mode as per your
thank
convenience.
you, thank you. So now let me share my screen once again, the entire screen, and please tell me whether it is visible to all of you or not. My MATLAB window is visible?
Yes, clearly visible.
Fine. Okay, now let us start. If you remember the dual two level inverter operation, here we have, let me increase the size of this. I think it is clearly visible that inverter 1 at the left hand side, inverter 2 at the right hand side, and open and winding induction motor in the middle having 6 terminal A1, B1, C1 and A2, B2, C2. The very simple logic we have implemented in the MATLAB, and I always used to say to my student, before pressing this run button, my cursor is at pointing to run. So before pressing run button, you must know the expected result. Then only you can understand the MATLAB. So if the logic is clear, then MATLAB is very, very simple. Otherwise, you will be in trap. You just keep on doing something, and the result sometime it come right or sometime it is wrong. Then we used to say ki result is not coming, result is not coming. So we will see how simple inverter we have developed. Now just double click this block. Here all 6 devices 135, 462 and 1 DC link is there, and 6 pulses are there, and which are demux and going to all these devices 135, 462, and all pole voltage are measured. And see, I would like to just tell the beginning of this, means which component is from which toolbox, because in yesterday, if you remember, Dr. Saurabh has already told you that now SIM power system is purchased by Opel RT. So This the entire simulation is made in the SimPower system, and hardware implementation and real-time simulation is carried out on the Opel RT. So when you open this library of MATLAB, then the simling, all the control signal, right? All the control signal is to be taken or to be developed using these block, simling block, right? You can say it is like this. For example, when we measure the voltage using the multimeter. So exactly what happened? There are two leads which are to be put it in the phase and neutral. Now inside that voltmeter there is some sensors, right, which convert or from this 220 volt into lower level signal, and those lower level signal you can see on the LCD of the your multimeter. So the same way, the triggering circuit of thyristor, IGBT, MOSFET or any power electronic devices must be for 10 to 16 volt, right? And if it's thyristor and all those things, then the gate pulse is to be provided to the thyristor, and it is the current control device. Means once it is on, it lose the control over the its conduction. Right, I am not going to fundamental of all those things. So control signal must be from the simling block, and the power signal means your IGBT, your power source, your transmission line or the motors, everything has to be taken from the same power system. This everything has to be taken from the same power system. I hope it is visible to all of you, although it is small, but I hope it
Yes,
is.
sir.
Oh, fine, fine, fine. So you can see electrical sources are there, elements are there. If you go to the machine, all type of exciting system and everything, power electronics, diode, GTO, IGBT, all devices are there. So these are very basic things, and we must know. Right, in case if you have any problem, you can contact me so that we can discuss and share the knowledge what little bit I have. So these devices which are looking in the yellow color, these are the IGBT, and it is taken in the SimPower system block set. All these measurement is from the SimPower system, and this addition block or these pulses are generated using the simulink block. Now let me go to the previous one, and this is the same type of inverter is this. Simple two-level inverter. Devices are 135, 462, 135, 462, the ceiling voltage, and pole voltage, and this addition of these pole voltage, or means all the things are there. Now come to the motor side. It looks like simple. See, when we did this simulation, this open and winding induction motor is not available in the MATLAB. You have to do the modeling of this. You have to do the modeling of this, right? But now the latest version, they have included the open and winding because of increasing demand in EV side and all those things, right? So this newer version, like I think 2021 or onwards, they have included this open and winding induction motor. But I prefer, rather than using develop a model from MATLAB, you develop its own. That will increase your confidence, and each and every point of the model you have full control. You can know what exactly the signal is generating or not, where is the problem. So when you click this, a huge model is open. And this is totally based on the simple equation. Simple equations of machine. Simple equations of machine, which I have shown in the modeling, that you have to take the ABC, then from ABC to DQ, then from DQ axis to go for the is D axis current, Q axis current, psi D, psi Q load, and each and everything has to be modeled. Right? I'm not going to detail of modeling of this because it is very simple modeling. No any complexity is there. Right? So that's simple modeling. As the voltage is coming from here in the signal form, the voltage is coming from here in the signal form, pole voltage, and that is fed to these motor model, and the torque and speed and everything is generated from here. Right? Here you can see. Clear? Now come to this is the power circuit. As of now, this is the power circuit which I have selected. Now job of power circuit is done. The rest thing is control circuit. So for control circuit, the simple logic is implemented. What we need to done need to be done, that three phase voltage are taken, and then find the maxima of that and the minima of that. Add these two quantity, take the negative sum and divide by 2 and add the reference signal VAVB. It will generate your space vector modulation based signal. But here what I did, see, this is the used scheme, means the scheme which I have already demonstrated to you. Then we have also developed the various other schemes, right? Like sinusoidal modulation, or the third harmonic injection modulation, or the selective harmonic elimination modulation. Different type of control schemes we have developed. Right? I am not going to see in this simulation 4 control scheme is being compared, but I am not going to tell all those, rather I should say not going to share, because the limitation of time. And to select this, no need to make 4 simulation. What I did, I simply developed 4 control scheme here using the same voltage. This slider gain, I'll tell you for what purpose this slider gain is used. See, we are operating this machine, this motor in the V by F mode. That means ratio of voltage to frequency has to be constant. Right? We have taken the voltage from here, then divide by the ratio, it will give you the frequency. So voltage and frequency, if you know, you can generate the reference signal. You can generate the reference signal Vm sine omega t, and 120 degree apart phase B and 120 degree phase C. All these signals are to be generated. So I am just demonstrating the used scheme which I have discussed in the PPT. Just see, it's a big simulation. That is why when I zoom out, it looks very small size. Now just see what we did. This is the voltage and frequency and simulation time. Why it is required? Because we have to generate sine wave. Sine wave means Vm is coming from here, right? Vm is coming from here. Then frequency sine omega t. Sine omega t means 2 pi f. F is coming from here. And omega ke baad, after omega t, the t is coming from the clock. All these things are available in your Simulink library. Just go here and see source. Other thing I would like to suggest, you should ask your student not to use this. What nowadays I have noticed from, in student, they simply start searching like this, and something come, and they use those now. It's my personal experience. Rather than using by this searching, you should try to find so that what happened if you do 2, 3, 4, 5 times, you also know the logic of that particular thing. For example, if you see this sources means they are generating the signal. Here just see, it is generating. Arrow is like this. From workspace, ground, all are like this. Just look the sink. You will find scope. The signal is coming. The signal is coming. All is like sync. They are absorbing the signal. So you should ask your student to try to first understand the various library and their use, then apply in the real problem. Okay, now come to the here. So what I did, this is the function. Which function I have taken? This is the embedded function, user defined function. If you go in the Simlink, in the Simlink, user defined functions are available, and that's very simple code is written. We have three input, VFT, and three output, VA, VB, VC. So V sine 2 pi FT, then plus 2 pi by 3 and minus 2 pi by 3, right? So that is written. Now our three reference, not reference, our three sine waves are generated, VA, VB, VC. Now we have to find out the maxima of VA, VB, VC. We have to find out the maxima of VA, VB, VC. Here we can have, there is a block, math block, that find the maximum of these three signals and maximum of these three signals. It will give you the, VA, VB, VC are three signals running in the same time domain, and the value, the value which is having higher amplitude, that will be outputted here as a maxima of VA, VB, VC. Likewise, the value which is having minimum of this, that will be outputted through this, that is the minimum. So maximum plus minimum is to be added, and after that minus half. Why it is? If you remember, it was negative of maxima plus minima divided by 2. So it is negative of maxima plus minima, and it is added to the sign, right? It is added to the sign of this, plus some constant, This is very, those who are working in the field of this power electronics, they know when we do the modulation, what we do, we simply put the sine wave in the middle of, let us say we have n level inverter, so we would have n minus 1 triangular, let us say it is 9 level. So you would have 8 triangular. Now you put your sine wave in the middle of these. That means from 0 upper 4 triangle, and from 0 lower 4 triangle, and you put your sine wave here. In that case, the switching losses are higher. Rather than doing this, what you have to do, first you put that triangle at the lower level. Means, let us say it is of 0 to VDC by 8. Let us say for n level inverter, each height is 0 to VDC by 8. Now, if the amplitude, the reference voltage is plus minus VDC by 8 up to that, then the sine wave must be put at the lowest angle. The moment it is increased from VDC by half of the VDC by 8, it should be VDC by 8 is to be added. Likewise, philosophy we have adopted, and the modulation signals are generated. I'll run the simulation in the end, then these things would be more clear. Here you can see, these are the three signals. These are the three signals which are generated here, means this is the 3-level inverter, means when the level 1, level 2 and level 3. Means when you require minus VDC by 2, then level 1. When you require 0, level 2. Then when you require VDC by 2, level 3. Likewise, three signals are there. And this is the multi-port switch. I'll tell you the function of this multi-port switch, even though most of the faculty already know. This is like something your uh, multi-port. Why we call it multi-port? Because it depends upon the this index value. It has three ports, 1, 2, 3. If this value is 1, it will output this. If this value is 2, it will output the second one. If this value is 3, it would output the third one. And what is in the third one? There are two switches combination. If you remember the two level inverter was left hand side and the right hand side. So for pole voltage, one has to be either plus VDC or 0, right hand side also at the plus VDC or 0. So two switches are to be operated and the remaining switch of that particular leg will be operated in the complementary fashion. If it is 0, then the lower switch would be 1 likewise. So that things are to be done. Now come to the again main circuit of this. Here again we did the same thing. As I told you, we have developed four logic here. At present, directly I am using the fourth logic, the pulse generated through the fourth logic. Here you can see A3 and B3 means for left side inverter, A3 are going, for left side, right side inverter, B3 are going. That means this signal is go to and here it is from. It is from. It is just for beautification, just to that your simulation looks very nice. Only for that purpose it is there. If you connect these 6 wire, then the simulation is very messy. That is why this type of things are to be done. So depending upon your choice, means if you say the value is 4, then it would become. Here the slider gain. The slider gain is available in the simulink itself. While running the simulation, you can change this. That is the beauty of slider gain. That is the beauty of slider gain. Now just run the simulation. Just run the, and for monitoring, we have also measured the phase voltage, phase current and everything. Now come to this and run the simulation. And I also make this little bit lengthy so that we can change the values and see the effect. Now I am changing the modulation index. Let us take 68, 60. Let us say 62, 63. No, 64. Okay. For voltage level, when I give 64, the modulation is coming at 0.8. Modulation is coming at 0.8. Similarly, let us make this 200. No, it is the over modulation range. 79. Just give me a second. 25. No. This, sorry. This is, even though actually, just give me a second. This is not the modulation index. This is frequency. Just give me a second. Just give me a second. This is frequency, not the modulation index. Frequency. This is frequency and lower one is the modulation index. Now run this, run this. Let us make this 8 point. Let us say make this 9.6, approximately 10. Then this inverter has to be operated as two level inverter. Since I have taken simulation time is quite long, just give me a second, otherwise I'll rerun this simulation. Okay. Just give me a second. It is opening. Okay. Now run this simulation. Now run this simulation. Here you can see the RMS voltage. Don't get confused that it is written as modulation index. Reason is this, that the display is being copied. That is why the name is repeated. Modulation index 3, modulation index 2. Basically, this needs to be changed. So that is very simple. You can change it like this. Voltage, right? Current. Very simple. Clear? Now, if you see the voltage, just see the voltage. This is the voltage. And here, if you remember that I was changing the modulation index. So the transient state is also showing. right? It keep on changing. Now I am going to take the modulation index high. I am going to take the modulation index high. For that, I am giving the voltage as 300. Once I give the voltage 300, modulation index is 0.75 and frequency is 37.5. If I give the modulation index we said 0.8, so let me give 400. Now modulation index is 1. Better I should make it 350 or 320. Fine. Now let us see. This is the zero point 0.8 modulation index, and when it was 1, the modulation index was then 1, then it was over modulation range. So let us see the voltage waveform profile. It was running for modulation index 0.2. You can see simple two-level inversion operation is obtained. At here, I have changed the modulation index. Just see the quality of waveforms. Here, some steps are missing, jumping from 0 to 200, whereas other places jump is from 200 to 300, 300 to 400. That means for here, the modulation index is as we have made the 1. So it is inverter is not operating in the multi-level inversion mode. It is operating in the simply two-level inversion operate mode. So now let me increase. Go to here, just go to here and see all steps are coming. Just see all steps are coming. Let me increase the, here you can see, of course its TSD would be less. Now how to check TSD? For that, this power GUI block is there. This power GUI block is there. And what you have to do, you just double click this power GUI block, and here it is FFT analysis. The FFT analysis is there, isn't it? This FFT analysis will give you the harmonic related information. Just click the FFT. Now I hope my screen is visible. Our new screen is pop up, and you can see the voltage signals are there, right? FFT analysis is not been done so far. So for that, what we do, just make it same as maximum frequency. Now just plus display. Rather than seeing the Nyquist, I am seeing the maximum frequency order, right? Now you can see these are the bar related to harmonic order. 0, that means some DC component is also there. Then third, fifth, 7, all order harmonics are there. Now just let me exclude the transient. Now I will take, because it is telling the average. Now I am doing from 2 point, or rather I start from third, and number of cycle is 5. Now just display the TLD is, and let us also display only the FFT window. Means I am taking the FFT of this. See, sometime our student get confused. Sir, kabhi hum ek cycle, when we take one cycle, then FFT is different. When we take 100 cycle, FFT is different. No, it is not the case. FFT remains same whether you take one cycle or 100 cycle. It is not like that. Slightly variation is there just because of this from where you are starting. That introduce the unsymmetric nature, right? So it is not the case. If you see These are the harmonic. Fundamental is 50 hertz. Now let us see the list related to fundamental. That also you can check here. Just, just here you can see the DC is 0.01%. No problem at all. Third harmonic is 0.73%. 0.73%. The dominant harmonic is fifth harmonic 0.31%. Seventh harmonic is 0.11%. And rest harmonics are very less. Remaining harmonics are very less. Now I take the maximum frequency as 2000. Now you will find that near 1000 hertz there is dominant harmonic. Let me first make it bar and let us display. Then you can see, here you can see it is the maximum related to this, somewhere around 48, 49. Let me take this as list related to maximum. Now I'll show you. Just see here. Just see here. H49 is 11.14%. H49, harmonic order 49 is this. Now, I also know that harmonic order, the frequency is 40. The frequency is 40. The maximum frequency is, we have considered 2000. Now just make it 2500 and see the next harmonic which is dominant in nature will occur H51. That means the 50th order is, frequency is 40. So the 50th order is, the maximum frequency corresponds to 2000, which is the 50th order. 50 into 40, that is 2000. So maximum frequency was order of 2000, and the sideband of 50 is 49 and 51. So the dominant harmonic occur at the sideband of the 50th harmonic. Sideband of the 50th harmonic. So all this thing, if we understand, then only we can teach our student, right? So this is all about this. Now just take the another example. Again I will ask, are you enjoying this, or I should explain some more on 9 level or higher level of inverter on the PPT? So just choice is all yours.
Sir, we are enjoying very much.
So I will continue with this and I'll show you the performance of 5 level inverter and see how simple it is. The very simple 2 level inverter, you just keep on extending this. One of my research scholar, and he is the co-coordinator of this event as well, Mr. Astos, he is working the same configuration on the 5-phase induction motor. We have, of course, the work is still pending on the experimental validation part. But as far as simulation is concerned, we got very good result. The same open and winding induction motor is used, and simple 2-level inverter we have applied, and we get very good performance, especially at the lower speed range, which is very difficult to have. Now let me open this 5-level inverter. Just give me a second.
Sir, I have put a very small query. Please go through it.
Yes. Yes, please.
I have typed in a chat box. that why this THD is 18% or more than 18% for 40 hertz frequency.
See, this 40 hertz, it is for three level inverter. It is for three level inverter and the switching frequency is 1 kilohertz. When we go for normal two level inverter, switching frequency is quite high, 5 kilohertz, 10 kilohertz. And at the same time, if the switching frequency is high, you got the higher switching losses. So efficiency of the inverter goes down. We have used only 1 kilohertz. I'll show you in the simulation. Just very good question. Just wait. I'll show you here. Just see this was the simulation, na? Just give me a second. Here pulses. These are the pulses which we are generating, na? Just see. Just see the switching frequency. 1 by 1000. The triangular pulse frequency is 1 by time period, that is the 1000. That means we are generating the switching pulses with 1 kilohertz switching frequency, which is quite low. Which is quite low. At that much frequency, you got this much TSD. Of course, if you increase this frequency, you get good TSD, but at the same time, there are switching losses. So you should compromise between the switching losses and the quality of the output. Clear?
Yeah, thank you. Thank you.
Welcome. And it is very good if you ask now in between. Because आखिरी में बात happen कि second speaker का time होता है, then we are in a hurry. So it would be
No,
great.
we don't want to disturb you. It was a very good lecture, so we don't want to disturb you. You can carry on.
Okay. Thank you. So let me start with this 5 level inverter. Let us take the or just give me a second. I should go from there and ask. Check. Okay. Again, the very simple logic we have implemented, the same open and winding induction motor model. I'm not going to discuss this again. And now we have two level inverter. One is 3 level inverter, other one is 2 level inverter. Now just check how we have developed. Oh, very simple. One 2 level inverter in cascade with another 2 level inverter. If you remember my PPT, just cross check. Look at this. The simple two level inverter. Via this, we are getting the 3 level inversion operation, and right hand side is 2 level inverter. The same things we are doing. Clear? And you can see the voltage level. This is VDC by 5. Then this was the 2 VDC by 5. Let me just VDC by 4 and 2 VDC by 4. Means whatever the value of this, double of this. This is 300. This is 150. And just check the other inverter DC link, it is 150. So the total value of DC link, whether it is a 2-level inverter or it is a 5-level inverter or it is a 3-level inverter, the DC link voltage remains same, that is 600 volt. Right? Actually, the motor which we have selected, for that this must be the requirement of this DC link. It comes somewhere around 539, 561, I think. So we have opted this 600 volt. Clear? Now, what we did here, as I said, in case if you require, you are going to develop uh, n level inverter, you require n minus 1 triangular pulses. Clear? So just see, we require n minus 1. This is the 5 level. So 5 level means you required 4 triangular. 1, 2, 3, 4. I suggest rather than using different triangle, you use one simple triangle and provide the offset. This why we are providing this offset. I hope you remember, as I told you, that since we don't want to put our triangular in the middle of the triangular, we don't want to put our reference signal in the middle of the triangular. What we do, we put it at the, for lower modulation index, we put at the lower side, I mean the first triangular, then for second, then third, and it keep on increasing at the upper side. So for that reason only we did this thing. Now come to the simulation part, and here again we have used the this multi-port switch just to select the mode. Here you can see this is the profile for acceleration. We increase the modulation index from 0.2 to this 0.8, and this is for 0.8 to 0.2. Means 80 volt correspond to 0.2 modulation index, and this 320 volt correspond to for this modulation index 0.8. Clear? So now let us run this simulation. One is the normal mode. First we run it at normal mode, and just check where is the simulation. Okay, this. So we will give at this as 80. Just let me check. It is 80 and 320. So we will start with 80. We will start with 80 and run this simulation for 5 seconds. Now run this simulation. After this, make this 320. Oh, before I make ये simulation end हो गया. Just check where all 3 triangles are. Here this is the normal mode. Here see the condition of all the, look at this. Look at this. This is the normal PWM which we do. This is the normal PWM. Let me stay to one side. This is the normal PWM which we do. You can see there are 4 cycles, and we put the triangular at the middle of this, right? But the topology, the switching or control algorithm which we have developed, we use this DC shift algorithm, and here if you see, it would be at the bottom. Look at this. It is at bottom. The advantage of this is lower switching loss. The inverter which is having higher DC link, that switches less. That is the advantage. So inverter efficiency get improved. Now I'll show you the result. Let me check. This is here, and just monitoring block is showing the waveform for voltage and current. Wonderful. Two-level inverter operation is achieved at lower modulation index. Now what I am going to do, I am going to increase the modulation index. I am going to increase the modulation index by 320. Now let us make this 320. Huh? Now run this. See the quality of output, voltage and all. Just see. Going towards sinusoidal. That is the aim of multi-level inverter. But still, if you find that the TLD is not less than 5%, it will be little bit higher. Anyway, this is the, good as compared to the previous one. So this type of simulation we can carry it out. Now I just show the various configuration. I just show the various configuration because time is very few minutes are left. This is the 9-level inversion operation. The same topology is extended and giving it the 9-level inversion operation, and we get the all switching pattern and everything, and see the how the drastically these switches are reduced. Just see. Just see. You required 168 clamping diode, but here in our topology, no clamping diodes are required. You required VDC by 8 IGBT in NPCFC and CHV, whereas ACHV use 12, but our use 6. Likewise, the great advantage. And this is the space vector of 217 switching combinations are there in the space vector. And these are the 8 triangular. And here how the variation of this DC offset based switching topology you can see. It is like this. Space vector based PWM, right? And these are the experimental result. And another topology I would like to show you, that is this. Here we have further reduced the DCE link. They are required for 8 DC link, 4 DC link, and now it required only 2 DC link. And the same result we got in this, right? And the major part is its capacitor balancing. You have to measure and balance the capacitor in every sample time. As the time is very less, so it is not possible. I am just skipping all these slides so that at least all these slides come in the view. And in future, if you feel that it is good or is related to your field, you can contact me and we can share the knowledge what I have and what you have. Right, and here you can see the capacitor balancing logic in this, how beautifully it is managed. We have disabled this capacitor voltage balancing logic. It is increasing. The moment we enable, it is automatically come at the level. So in the conclusion, I can say we have studied 2-level inverter, 5-level inverter, 9-level inverter, and hybrid 9-level inverter. And a different hardware component we have seen in this, along with the isolation deadband circuit and voltage current sensor. Although I am not able to show you the isolation and deadband circuit because of limitation of this time. And one slide I would like to show you all and feel it. Not only watch this, just feel that is शिक्षक कभी साधारण नहीं होता. प्रलय और निर्माण उसकी गोद में पलते हैं. This statement is from Acharya Chanak, because if you are not extraordinary, you can't create extraordinary student. So as you are the faculty, you always remember that you are an extraordinary person. Then only you can create extraordinary person. Otherwise, it is very difficult for us to create extraordinary student. We are here to create extraordinary students. So with this, I end my talk, and this is my detail, like my Insta profile, and this is my channel ID, Power Electronics by Dr. Sanjeev sir. All the lecture which I used to take at different institution or for my BTech student or PG student, that I uploaded here. So with this, I end my talk, and it's 5:30. So over to you. If you have any question, you can ask.
Dear participants, if you have any query, you may unmute and ask the questions.
Hello, sir. In chat box, question asked there. In chat box.
Okay. I'll check. One is Shashi is asking, please share the feedback link which we have already shared, right? And can we add multi-level inverter topology? Of course. For power quality, it can be used. One of my research scholar is use solar power based grid type system where we use multi-level inverter. In the same way, the open and winding motor, we use the transformer which is open and winding based, and we try to feed the power through multi-level inverter. Then next is, dear professor, why this 18% TSD? Oh, this I have already answered. That the TSD is high because we are using the switching frequency of 1 kilohertz. Then Mr. Harsh Jain, it's really appreciable how you are encouraged and make models on our own instead of using. Okay, thank you, Harsh. Then Harsha ji is visible now. I don't think so. Any other question from there? MATLAB now. Okay, I have already.
Hello, sir. I'm here, sir.
Yes, Guru Swami sir. Bataye, please.
Yeah. The session was very good. Then I think probably I'll switch over from the DC-DC converter to multi-level inverter. You're all doing with the multi-level inverters. Now I'll go for the induction motor drive by considering the multi-level inverters.
Great, sir. Then definitely we can do something great.
Yeah, because I teach the subject of the electric vehicles in which we normally replace the DC motor by the permanent magnet synchronous motor, where it requires the inverter control. I think probably whenever I get some kind of doubt, probably I may approach you, sir, in future.
My pleasure. Pleasure is all mine.
Okay. Thank you very much, sir.
Thank you. So, Astos, I should leave?
Okay. 1 second. Respected sir, on the behalf of organizing team, I extend my heartfelt vote of thanks for the highly enriching session on the topic MATLAB simulation of reduced device count multi-level inverters for electric vehicles. Sir, your lecture was extremely insightful and technically stimulating. The way you elaborated on the concept of reduced device count multi-level inverter topologies and their significance in improving efficiency, reduce cost, and enhancing reliability in electric vehicle device was truly commendable. Your detailed explanation of the open and winding multi-level inverter topology provided us with the deeper understanding of advanced inverter configuration for EV applications. The live demonstration of MATLAB simulation added immense practical value to the session. Seeing the modeling, waveform analysis, and the performance evaluation in the real time made the concept much clearer and more impactful for all the participants. Your expertise, clarity of explanation, and research-oriented approach have greatly benefited everyone attending this FTP. On the behalf of organizing team and all the participants, I sincerely express our heartfelt gratitude for your valuable time and knowledge shared with us. Thank you once again, sir, for much more informative and inspiring session. Thank you, sir.
थैंक यू डियर. 5:40 से मैं कन्वेनर के रूप में आ जाऊंगा. सो आई एम नॉट लिविंग एंड आई से कि आई मीन none of us should leave. Thank you very much. We will start at 5:40 after 6 minutes. Thank you very much.
Thank you.